Well, hello everybody. In this screencast, we're going to take about 10 minutes. We're going to look at how to make new functions from old functions. Most of this time will focus on transformations of functions. Some of our time will focus on composition of functions toward the end of the screencast. So let's talk about something that you have surely seen before. You have surely seen a graph like this, where we've got f of x is x squared, and then somebody goes ahead and graphs this, and you say, oh my goodness, it's got a -3 in it, and it moved to the right 3, and then you say, well, that couldn't possibly be a coincidence. And so you take a look at f of x is x plus 4 squared, and you guess, oh, you guessed right, it moves left 4 from this original position. And all of that indicates what we already know. We already know that f of x minus h is a translation of f of x by h units to the right. And you think to yourself, wait a second, you just hang on one cotton pickin' minute. I've got some function f of x, and I want to move it. I want to fit, so this is f of x, and I want f of x minus 2. This minus, shouldn't that mean to the left? And the answer is yes, it means 2 to the left. But what gets moved 2 to the left are the axes themselves. And when the axes get moved 2 to the left, it appears that the function has moved 2 to the right. You're thinking, whoa, that's crazy. So I'll show you what I mean. So I'm just going to trace the f of x graph. Oh, that's awful. That is just awful. Let's move this out of the way for the moment. And let's combine these two things. Great. So now what happens? So you've got your f of x, and then you move it 2 units to the left. You move the axes themselves 2 units to the left, which makes the graph appear to move 2 to the right. And that's what's really going on with transformations of functions. Well, then you get the one that's pretty standard. You get the one where you say, okay, so I know what this does, and I know what this does, but what happens if I take that x squared and I add 2? Well, oh look, the graph goes up by 2. Or you say, what happens? Oh look, it goes down by 4. And so then you see something like this. F of x plus k is a translation by k units up. And you say, where's your axis trick now, Rooter? And I say, my axis trick is still right where it always was. So you've got y equals f of x. And in the first case, we replaced x with x minus h. And that got the axes to move left h, which made the function appear to move right h. But what if we replace y with y minus k? I mean, we replaced x with x minus h. Why not replace y with y minus k? Well, in that case, we get this. The axes moved down k. The graph moved up k. It's the same process. There is not a different rule for horizontal than vertical. We just look at it that way because that's how it's always been presented to us. Okay, so back to the drawing board here. So let's now take a look at what happens if I take that x squared and multiply it by 3. oh, look, the thing got skinnier. Or if I multiply by 0.25, well, the graph gets wider. But what is really happening there? What's really happening there is that when you multiply by some number c, you get a dilation of f of x vertically by a factor of c. That is to say, this 3x squared graph, this guy, is a vertical dilation. Imagine grabbing the blue graph from the top. You know, you're a giant angry gorilla at the top of the y-axis, and you grab that function and you pull in the vertical direction until all the y values are stretched out to be 3 times as big as they used to be. So instead of 1, 1 on the blue graph, you're at 1, 3 on the red graph. Instead of at 1, 1, you're at 1, 3. The graph stretches in the vertical direction by a factor of 3. Similarly, on the black graph, the y values are dilated by a factor of 1/4. So the y values are all smaller, which makes the graph appear to be wider. Likewise, f of x over c is a dilation horizontally. So what does that mean? Well, that means that if I replace x with x over 3, I get a dilation horizontally. Instead of being at 1, 1 on the blue graph, I dilate horizontally. Now I'm at 3, 1 on the red graph. The dilation is horizontal. So you could talk about the graph getting wider because it was dilated vertically by 1/9, or you could talk about it being dilated horizontally by a factor of 3. Okay? Okay. Other things you should know. You should know what composition is. So let's just pretend, pull out the little red trolley and pretend that I have some function f of x and it's x squared, and I have some other function g of x and it's x minus 3. What does this mean? Fog of x. Well, fog of x, and that's read f of g of x, all that means is that we're going to take f of g of x, which means that we're going to use the f function, and the f function squares an input. The f function takes whatever the input is and squares it. And we're going to let that input be g of x. Well, what's g of x? G of x is x minus 3. Now, everybody look at the, oh look, we're squaring. Everybody look at that and say, oh look, we just square both sides. We just square both pieces. Now everybody look at that and scream at your computer monitor, because this is a travesty right here. This is never going to happen in our class. Got it? Got it. This is x minus 3 times x minus 3, and if you were to multiply those together using whatever process you use to expand brackets, you end up with that. Similarly, we could talk about gof of x, and gof of x is g of f of x. So we're going to take the g function. The g function takes whatever the input is and subtracts 3. So what's the input in this case? The input in this case is f of x, that's x squared minus 3, and we just write it like so. To which you say, wait a second, them are not the same. Right, them are not the same. Composition is not generally commutative. Okay? Okay. So that's all about new functions from old. Glad you watched. See you soon.